At that moment, I am describing some properties of modulus, of complex number. That means we can write out that one as a few properties of moduli. Okay, but moduli. Next one, if we have suppose three complex numbers Z1, Z2, Z3 are the complex numbers given. The first one property, that is modulus of Z is equal to 0. That implies Z is also equal to 0. That means if our modulus is equal to 0, then we have the complex number is also equal to 0. How we can prove it? Let x plus iy is equal to z. Then, as we have modulus of z is equal to 0, that also implies x plus iy is also equal to 0. That means we are proceeding with its modulus. That means x plus iy is equal to 0. Writing that one, x square plus y square is equal to 0, which implies that is only possible if we have x equal to 0 and y equal to 0. Now, when x equal to 0, y equal to 0, x plus iy, that means we are writing that one as 0 plus I into 0, or that one is 0. So simply that implies x plus iy is equal to 0. So that is the first one property we need. If we have the modulus of any complex number is equal to 0, the complex number itself is 0. Next one property, that is very important. That is property 2. The complex number into its conjugate is multiplied, then that one gives us the square of the modulus of the z. Okay, let's check how to prove it. Let z is equal to x plus iy. Then its conjugate z bar is equal to x minus iy. Let's multiply it. So z into z bar, which gives us x plus iy into x minus iy, or which gives us x square minus I square into y square, which means x square plus y square. Now that x square plus y square can be written as square root of x square plus y square its square. Now, what is the meaning of that square root of x square y square? That is also gives us the modulus of z. So simply we can write that one as modulus of z its square. So that means the second property, z into its conjugate when multiplied gives us the square of the modulus of the complex number. Third one property, that is property 3. The modulus of a complex number and its conjugate is same. That is, if we have modulus of z and modulus of the conjugate of z, both are same. Already that has been proved in some problems, but once again, let uh, x plus iy is equal to z. Hence, z bar or conjugate of z is equal to x minus iy. So if we want to find out the modulus of z, that gives us square root of x square plus y square, and also the modulus of z bar is giving us x square plus y square. So simply it gives us mod of z is equal to mod of z bar. And last one property, which is also very important, that is property 4. The modulus of the product of two complex numbers is equal to the product of their moduli. Okay, and that means if we have modulus of z1 into z2, that means modulus of z1 into modulus of z2. Let's check what is happening here. We have modulus of z1 into z2. We can write it as z1 into z2 into z1 into z2 its moduli. Let's check what is happening. We have from the property 2, look at the property 2, z into z bar is equal to modulus of z square. z1 modulus of z1 into z bar is equal to z bar whole square. So here we are wrong. That must be like that. z1 into z2, its modulus whole square is equal to z1 into z2 into its conjugate. Next one, as like whatever be in the first portion, we are writing here. No problem. Next part, z1 into z2 bar, which can be written as z1 into z2 bar. That means if we have z1 into z2 bar, that means conjugate, we can write it as z1 conjugate into z2 conjugate. That is also true from the property of the conjugate of complex numbers. Then we are proceeding here. Now, that one, that means we are here writing z1 and z1 bar here, taking z1 into z1 bar and that one into, that means z2 into z2 bar. Now the same thing is happening here. That means Z1 into Z bar is equal to Z bar square. So we can write it as Z1 square into Z2 square, which implies, that means both are squares are here. So that implies Z1 into Z2 is equal to Z1 modules into Z2 modules. In general, practically what happens if we write it as general? In general, if we have Z1 into Z2 into Z3 into Z4 into Z5 into Zn, the complete multiplication of all the complex numbers and finding its modulus, that means it can be written as each and every complex number modules as the multiplications. That means module of Z1, module of Z2, module of Z3, module of Z4, module of Z5, up to whatever we have taken, module of Zn. First, another one last thing, that is we can say as corollary, if we have Z1 is equal to Z2 is equal to Z, then we can write it also from here that Z square its modulus is equal to modulus of Z into modulus of Z, or that is also square of the modulus of Z. Okay, that means you can write it as simply modulus of the square of a complex number, that is the left hand side, that one is equal to the square of the modulus of the same complex number. Here I am not writing the same what, okay, writing same. Okay, so always we have to remember that one thing, that is Z square its modulus is equal to modulus of Z its whole square. Another one small property is also there. Okay, as we are here, just write down. That is property 5 of the modulus, that is also important. The moduli of the quotient of two complex numbers is the quotient of their moduli. Okay, that means it is nothing, that is modulus of Z1 by Z2 is also equal to the modulus of Z1 divided by the modulus of Z2. Just that is the same as we are writing with the help of the multiplication form. Here we are writing it as the multiplication, that one is for the division form. Okay, if we want to prove it, that means we can write out it as modulus of Z1 by Z2 its square is equal to, write down as same as we have already, that is Z1 by Z2 its complete conjugate. Then we have different way, that is zy by z2 into z1 its conjugate, z2 its conjugate. Then write out, that is z1 into z1 conjugate, z2 into z2 conjugate, or we can write out the numerator as z1 whole square, denominator as z2 whole square. So from here we can say z1 by z2 is also equal to modulus of z1 modulus of z2.